Hello, Physics 2 students. In this video, I want to talk about electromagnetic waves or electromagnetic radiation. These are going to be wave solutions to Maxwell's equations, where the energy density will sort of slosh back and forth between electric and magnetic and back to electric and back to magnetic and back and forth and back and forth. But to get a sense for how that could possibly take place, let's imagine we had an AC power supply and we hooked it up to, I don't know, it could be a wire or anything. And what's going to happen is as the power supply oscillates, you're going to get charges moving around in this wire, and it effectively sets up a time-dependent dipole. So you could say at this time, at the beginning, let's say there's a positive charge here at the top and a negative charge effectively here at the bottom. And what we can do, one way we can see that there could be a wave type solution is to kind of sketch in that moment what the electromagnetic field lines should look like. They'd look something like this, running from plus to minus. Now, if you wait a little bit of time, the effective dipole moment is going to be smaller. And so we're going to effectively have charge, say plus here and minus here. So now the field lines, remember they can't cross. I've already generated these field lines. And so they have to move off to the right so that I don't crisscross them. And if you wait another moment in time, you'll see that the negative end of the dipole will be on the plus side. And that's going to have the effect of pinching off these loops, creating new loops. And the old ones will be pushed off to the side. And if you do one more moment in time, we would now have electric field patterns like this. And these other original field lines have just keep getting pushed further and further to the side. And so you can imagine it's almost like smoke billowing off away from this antenna. You get these little bubbles of field lines that just kind of migrate off to the right. That's kind of an interesting picture. And it turns out to be pretty accurate. What about magnetic field lines? Well, let's go back and think about Maxwell's equations now. So we want to solve the equations in vacuum. So we're not going to try to solve these near other charges because that gets really complicated. So we're going to imagine you're out in vacuum. And in that case, we have del cross E equals minus dB dt. And similarly, we have del cross B equals mu naught epsilon naught times the time derivative on E. And when you put these all together, what they suggest is that first of all, it suggests that the electric field and magnetic fields are perpendicular to each other. It also suggests that they are both perpendicular to the direction where the spatial derivatives seem to be acting, namely the direction that the wave is moving. So if you had a wave moving in the x direction, the electric and magnetic fields would only point in the y and z direction. Going back to our previous picture, what this would suggest is that if I have an antenna configuration like this, then, and let's imagine I had some of these little electric field loops. It suggests, if these are my electric field lines, it suggests that my magnetic field lines would look like maybe something like this. They would be perpendicular to the field lines, the electric field lines. So the magnetic field lines and electric field lines are perpendicular to each other, and they sort of do this dance, whereas one increases, the other decreases. Anyways, there's a synchronized way that they rise and fall. Let me just say it that way. And they are both perpendicular to the direction that the wave is propagating. So these are kind of pictorially what you have. I'm going to give you, we're going to work through the differential equation, and then we're going to see the actual wave equation emerge. And then we will, I'm going to use an animation I found off Wikipedia, which does a much better job than my artwork can at showing you what this stuff looks like. All right. Okay, so before I get too far into this, I need to remind you of a vector identity that hopefully you learned in Calc 3, namely the curl of a vector equals the gradient of the divergence minus the gradient squared. It's like the dot product of del with del acting on V. Okay, and that's true for any smooth, differentiable, nice vector field. So I'm going to use that on my two Maxwell's equations. So the first equation says del cross E equals minus dB dt. And then del cross B is mu naught epsilon naught dE. So what we're going to do is take the curl of the, we're going to take the curl of the top line and then substitute in what we get. So we're going to take the curl of the top line and we're going to get del cross E equals minus partial restricted time of del cross B. This may be written as del equals second time derivative acting on the electric field. And this first term is 0 in vacuum. Remember, Gauss's law in differential form says that the divergence on E is the charge density, which we're taking to be 0 over epsilon naught. So I'm left with the following equation. 0 equals mu naught epsilon naught partial with respect to time squared acting on E minus gradient squared acting on E. This is nothing other than a wave equation. And you might remember from our video on wave equations, the coefficient of the time derivative is related to the velocity. In particular, what we find is that the velocity of this wave must equal 1 over the square root of mu naught epsilon naught, which you type in numbers, we get 3 times 10 to the 8th meters per second. It's the speed of light. So waves of electric and magnetic fields are the same as light. This was a total surprise. My understanding is Maxwell worked out his theory. He figured out the complete equations for electricity and magnetism. He then found these wave equation solutions, these wave solutions. And his first thought was, oh, well, what are the speed of these waves? And he plugged in the numbers. And at that point, he realized that it was within, the margin of error of the speed of light, which was only a relatively, recently known number for him. So this is not an input into the theory. This was actually a discovery he made, and he made it through theoretical considerations. So speed of these waves is the speed of light, and we make the identification of waves of electric and magnetic fields are light waves. You can go through the similar kind of analysis and find the same exact differential equation for the magnetic fields. Okay, so both electric and magnetic fields satisfy the same wave equation with the same speed, which is nice because that means that you're not going to have a situation where the electric part outruns the magnetic part. They move together with the same speed. All right. Well, all right. So as these are wave equations in 3D. So these are 3D wave equations. There are many solutions. It all depends upon the details of the charges and the sources and the currents and the wires and this and that, the antenna arrays. Every antenna array would have a different type solution. We're going to focus on special, called planar solutions, or plane waves. And these are waves which move along one axis only. So that means the wave solution will depend upon, well, we're going to take it to depend upon the x coordinate, which means it is independent of y and z. And because it is independent of it, if you were to plot level curves of wave intensity, they would sweep out planes. So that's why they're called plane waves. So we're looking at waves of constant intensity, where if I kind of drew a sheet of constant intensity, it would look like a plane moving, say, to the right, for example, at the speed of light. So these are going to be planar waves because the wave fronts look like planes. All right. So these planar waves, because they only depend upon one coordinate, have a lot of similarity with our 1D waves from before. In particular, the general solution then is going to be of the form some constant vector amplitude sine k x minus omega t. This is going to be for a right moving wave, planar wave. And similarly, we'd have for b equals b naught times sine kx minus omega t. Where, as with the 1D waves, we must adjust the parameters k and omega such that omega over k must equal the speed, which is c, or remember we had these other quantities. You could define lambda, which was 2 pi over omega, and you could define the period, which was 2 pi, sorry, strike that backwards. 2 pi over k, and you could have period, which is 2 pi over omega. And you could also, that would work as long as you said that c equals lambda over t, or c equals lambda times the frequency f. 1 over the period. All these are equivalent statements. Okay, and we will freely go back and forth between different forms. But really, there's no difference at this level between the 1D waves that we had. Now it just looks like we have two vector waves, and naively at this point, it looks like we have three components for the electric field. Sorry, not three, two components possible for the electric field and two components possible for the magnetic field. I only have two possible for each because they both must be perpendicular to the direction of wave propagation. So they have to be perpendicular to the x direction, which means they can only be in the y or z direction. However, it's not quite that arbitrary. We still have to solve the relationship between E and B. The wave equation that I wrote down here, well, here for the magnetic field, mixes or only relates components, time derivatives of magnetic field to spatial derivatives of magnetic fields. But we can't really forget that there's a connection between electric and magnetic fields. So, in that because the relationship says that del cross E is minus the time derivative on the magnetic field, that means that, well, we can just work this out. Maybe that's the best way to do it. So what we're going to do is we're going to take E, we're going to choose our coordinates in the YZ plane so that E lies along the Z axis. And then we're going to plug this into our ansatz here. And we take the curl on this. That's going to give me minus, it's going to be a y hat, and it's going to be the x derivative on this. It's going to be k times e naught cosine. On the other hand, if we make the guess that b is just some vector b naught times sine of kx minus omega t, then the time derivative on b is simply going to be b naught times minus omega cosine of kx minus omega t. So if we equate del cross E with minus dt on B, we end up with in the y direction curl explicitly evaluated on the electric field must be related to the minus the time derivative on the magnetic field. That's going to be omega equating both sides tells us that the polarization vector for B, the magnetic field, must be um, the magnitude of the electric field times the wave number of the electric field divided by the frequency times y hat. If you think about that, that's nothing other than y hat. So pulling this all together, we get solutions. We get an electric field, which is equal to E naught in the z direction, cosine of kx minus omega t. We get magnetic field solutions, which are E over c times y hat cosine of kx minus omega t, and the waves move in the third direction, the x direction. So I'm going to switch over and show you an animation I found on Wikipedia that does a good job of showing what this looks like. Here's the picture we have. I know it's a little blurry, but I stretched it out to make it larger. What you have is this is a wave moving. Okay, this is along the y-axis, but the idea still stands. And what you find is you get oscillatory regions of electric and magnetic fields, and they are always perpendicular to each other. And it goes, and it just goes on and on and on like that. This is the picture of what light actually is. I would try to draw that, but it would just get really ugly. Some different comments. There are, so as with all waves, with all sinusoidal waves, we have different wavelengths and frequencies. So all we have to do is make sure that the speed of light equals lambda times f. You can have any wavelength and any frequency as long as you keep this product fixed. If we rank different kinds of light waves from long wavelength, so we could have a long wavelength, which is low frequency, all the way to short wavelength, which would be high frequency. We would have radio, microwaves. We'd have IR, infrared. Then we'd have Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. So we'd have visible. Maybe just write visible. And then we'd have UV. Then we'd have X-ray. And then we'd have gamma. So each one of these is just, they're really all the same thing. They just have different wavelengths, and so they interact with different sized particles and objects a little more or less efficiently. And so that's why we break them out and give them different names. Just another comment, or just a kind of a useful thing to remember, just to highlight, note, the amplitude on the magnetic field is the amplitude in the electric field divided by the speed of light. So it's just useful. It's one of those useful little facts that's kind of handy to just know, so you don't have to keep scrounging for little details. All right, so we've talked about electric and magnetic waves. We've shown how they are perpendicular to each other. We've shown an explicit solution, a wave solution. The last little piece for the course really is to talk about the energy flow, the intensity of light. And to do that, we use the pointing vector. S. And it's a convenient name because S points in the direction of energy flow. And it's equal to 1 over mu times E cross B. Now, I thought about trying to motivate this, but it's a lot of vector calculus identities to show that this is the reasonable thing. So you're going to have to just take it on faith. But this vector, what it measures is the rate of energy flow per unit area in a direction. Okay, so it's the energy per unit area in a direction, energy rate. So that'd be a power. So that's otherwise known as a power per area in a direction. That's what it's what we mean by intensity, the intensity of light. If we evaluate this on the plane wave solution, we would say S equals 1 over mu naught. And when you work that out, you're going to get E cross B. So that's going to be E naught times z hat sine kx minus omega t across the magnetic field, which was E naught over C times y hat minus sign. And we do z cross y gives us a minus sign. So we end up with 1 over mu naught times E squared over C sine squared kx minus omega t. And you use z hat cross y hat gives you x hat. And the minus sign goes away. Okay, so as advertised, this does indeed point in the direction of wave propagation. It has units of power per square meter, so watts per square meter. And those are the right units to be an intensity. So the brightness of light, okay? However, this isn't really what we should mean by intensity. When you plug in light, we see that for typical light, visible light that we are seeing, it has high frequency. So visible light very high frequency. So what that really means is what we perceive is not S. So we don't see S, but we really just see the time averaged value of S. So to calculate what we perceive as brightness or intensity, we should calculate the time average of S. Intensity should equal the average value of S. That's equal to times the average value of sine squared of kx minus omega t. And remembering our discussion of root mean squared and averaging oscillatory features, we see that we remember that when you average sine squared, you just simply get a factor of a half. So the intensity that we perceive is going to be given by the amplitude of the electric field squared over mu naught C times a factor of half. And that can be rewritten as E naught over mu naught times B naught over 2. Or if you prefer, you can think of that as the RMS values for E times the RMS value for B over mu naught, just like we did with looking at the average EMF in a generator, in an AC generator. So there we have it. So this gives us a description of light as a wave, and it carries energy density, and we've seen how to connect it to the everyday phenomenon of brightness and intensity. Well, it's kind of been a long journey here. And we're together through the semester or through half the semester, and then this last stretch here with me talking to you through these videos. So I I hope I've been able to convey the story of electricity and magnetism, kind of the intricacies and the way that it all hangs together, and I hopefully I've been able to convey how it's kind of an elegant theory in the end. When it all fell into place, all the pieces fit together just right, and it's a pretty slick, elegant theory of nature. So hopefully this has been a course that you've learned a lot, and hopefully it's stretched you, but not to quite to the breaking point, and it's made you better engineers and scientists. So thank you for the semester, and I'll see you around.